I'm Valentin. I'm a developer advocate for Google Cloud Platform. And today we'll talk about performance. And we'll talk about performance of programs written in Go running in a public cloud. I have a lot of slides, and I probably won't have enough time to answer live questions. But please come to me just after the presentation, and I'll be happy to discuss. First, I'll share my insights about what we want to optimize and why. Then we'll see how we can observe the performance of a cloud architecture and discover which components best explain the actual latencies experienced by our users. And finally, we'll have a look at how we can observe and improve our components written in Go. What is performance tuning? Usually, it's about working on something that is slow and making it faster. Pretty simple. Why are we doing this extra effort? Some possible benefits of improving performance is to increase the throughput and to decrease the cost. But today, I'm focusing on the most important goal, which is to offer a better user experience. Human seconds are more precious than machine seconds. Users have very high expectations of speed. And if they experience a sluggish service, they will get frustrated and they will leave. The architecture of a new software system designed for a certain level of performance is always the result of experience and intuition. They reflect what kind of latency we should expect in theory. However, measurements are more relevant as soon as a system exists, even before its initial release. And measurements often contradict intuition. I'm an experienced developer, and I have intuitions. Well, most of the time, they are dispelled by the actual numbers. So on one hand, I get frustrated that my super smart intuition turned out to be dead wrong. And on the other hand, I'm happy and grateful that my measurements finally provided me with insights closer to the reality. There is an interesting correlation between code quality and performance. When you successfully refactor some code to make it faster, you often to make it clearer and more decoupled, you often end up making it faster, as it's less cluttered with irrelevant instructions that were previously executed in vain, and also because some possible optimization now become more obvious and easy to implement. On the other hand, if you push further in your quest for performance, you will have to give up simplicity and resort to hacks. You will indeed shave some milliseconds. This is the green line going down here. But code quality will suffer. This is the blue line also going down now, insofar as the code will become more difficult to read and to reason about, more brittle, and less flexible. So it's a trade-off. How far are you willing to go? Now a word about automated tests. Designing strong automated tests is necessary in order to make optimization refactoring without introducing regression bugs at the same time. Do you know the difference between service time and response time? Anyone? Not that many people, that's great. These 100 milliseconds here are the time it took for the service to process an incoming request. This is the service time. But it might very well be that the latency experienced by the user was actually 700 milliseconds. The user may have a slow connection, or the request could be queued by some data center front end, invisible to the server instance until all the other queued requests have been served. This total latency is the response time, and it is always bigger than the service time, as it also includes the network round trip and the queuing time. In the point of view of your web server, you may be thinking, wow, each of my resources are served in 50 milliseconds or less. This is really efficient. That's 120 milliseconds for my total page having 3 resources. Everything is fine. And in the monitoring system, all the individual resource requests from all users may be displayed together in a complex interface. And when you click on a single request, indeed, everything looks fine. Well, not so fast. What the user really experiences is certainly not a meaningful page load in 120 milliseconds. Because of the current design of the page, the resources are fetched by 3 sequential requests, and the total response time is around 2 seconds. There is room for improvement, and the best fix is probably some client-server front-end work, and not the speed improvement of the existing backend endpoints written in Go. For example, inlining the most critical assets could result in a dramatically better response time. So why am I saying all this, and what does it have to do with Go programs? The point is that Go software is usually server components. The server components are where we have the most accessible information about performance, the server logs, the server traces, etc. But it's too easy to fool oneself into thinking that when the server is fast, then magically the whole system is fast and the user are having a pleasant, seamless, responsive experience. That is simply not true. This is how, looking only at server latencies of an internal application at Google, I didn't even notice that an important page was taking 30 seconds to render. The users were staring at a blank screen, completely unresponsive, while the JavaScript was performing UI repent over and over for some reason. And that was completely invisible to the server monitoring. The first step to achieve some meaningful and valuable performance is a sane architecture that takes into account the client device workload, the browser cache, the network latency, and the number of round trips between server-side and client-side. Ideally, we should use a RUM system, real user monitoring, to have the browser collect valuable metrics, so we don't have to rely only on the server metrics. In the recent years, quite a lot of the workload and of the latency has shifted from the server side to the client side, and we have to take this fact into account. More generally, focusing on the users is a good idea. I can't overemphasize this axiom: users first. Now let's have a look at the observability tooling available in Google Cloud Platform. The Cloud Web Console includes StackDriver logging, which consolidates the request logs and the applicative logs of your compute components, so Compute Engine, Kubernetes Engine, the serverless components, in near real time. You can filter the view by component, by keyword, and by date. For each request, each line is a request, you can see the full URL, the size of the payload, the timestamp, and the latency. The latency is, of course, the service time. It's super useful, but remember that it's only a fraction of the response time. Some of the App Engine standard requests have been automatically instrumented. If we click on the blue link in the latency column, we will see the waterfall view of all the API calls that happened during the processing of this request. I love waterfall charts. They provide with so much insight in a single view that I'm even okay when they're telling me, you were wrong, this is what really happened. Okay. The StackDriver trace view, integrated directly in the GCP web console, shows me for a given request what API calls were made, in which order, how long they took, and if they were sequential or concurrent. The top right button shows the applicative logs right inside the waterfall diagram. This is actually a great feature for observability. The spans tell me what happened, and the logs tell me why. In this specific example, the total latency of 62 milliseconds consists almost entirely in one data store entity read and then 2 data store queries. We have a few read and write accesses to memcache, but those are super fast. Now I know that the bottleneck is the data store, and there's no point in trying to speed up my memcache operations. You can also notice that the last two data store queries run concurrently, which is a good idea when it's possible. I strongly encourage everyone to set up the automatic export of all the logs to BigQuery. Such an export is also called a sync. With BigQuery, you don't have the default retention period of 30 days only, and you can use SQL to query fine-grained performance insights over a large or short period of time. Can we please switch to the demo computer? So I will show you live in my browser. This is a backend of a website written in Go, running on App Engine standard. In the latency column, the static assets, 1 millisecond, have extremely low latencies. They are actually served by an internal CDN. And here, if I click on the blue link of a request to view the trace details, I will see the API waterfall. So this one just consists in 2 sequential data store query. OK, fine, nothing fancy. If I want to find something that took longer, I will filter, show entries with higher latency. OK, oh, this one was not really fast. What was it about? OK, memcache, data store, something that can be either some processing or just some serverless weirdness. OK, I already have a sync to BigQuery properly configured. Here it is. So I can ask questions in BigQuery, like in April, for all the requests that were not made by a bot, because I don't care about search engine bots, and that were not static assets, so they don't start with this prefix. What were the requests that were the most frequently accessed URLs, and what are their average latency and their highest latency? Let's run this SQL query in BigQuery. We should have an answer in OK, so the home page / has been the most accessed page. The average latency was only 5 milliseconds. No, that's not better. Only 5 milliseconds. That's quick. And the max latency was about 400 milliseconds. OK. The secondly most frequently accessed page was the RSS endpoint, which is not really user-facing, but it's usually fast. But sometimes it can take up to 2 seconds, 1.7 seconds. Maybe I should have a look to see if I can speed that up. There are some cases where we'd like to insert our own spans in the trace waterfall. For example, if we have a CPU-heavy computation, or to show the duration between 2 related events. OpenCensus lets you do this with its StackDriver exporter. And the Google Cloud documentation shows how to do this for App Engine Standard, for App Engine Flex, for Compute Engine, and for Kubernetes Engine. OpenCensus and its competitor OpenTracing are open source. They have recently joined forces. The APIs will converge. And this is great news for the cloud computing observability community. Conceptually, the best view to understand the latency of a component is a waterfall view. In this simple example, 100% of the server latency of a request, service time, not response time, consists in 6 sequential calls to external services. The service works well, but everyone agrees that it is a bit slow, a bit sluggish. Here, I can see 4 opportunities for improvements. First, I now have a better idea of the latency of each of my dependencies. If my database is expected to respond in under 100 milliseconds, but my measurements show that each query actually takes 200 milliseconds, then I know that something should be fixed in the external database. Maybe create an index, If I'm lucky, I just sped up the database accesses without changing anything in the server code, only by doing hops on the database. The total latency has just been reduced a bit. It's no longer 900 milliseconds. I often witness repeated access to the same service with different parameters and payload. It is a law of the universe that if the service accepts batch calls, that is, if it accepts many commands in a single API call, then the batch call will be faster than the sum of the individual calls. Here we are calling service B 3 times sequentially with different parameters 1, 2, 3. But we can do better. By transferring the same amount of inbound and outbound data and asking for the same amount of work to the service B, but in a single API call, we suddenly improved the total latency. This may sound counterintuitive, but it makes perfect sense because some heavy costs like the network round trips, the network latency, component authentication, etc., are now paid only once instead of 3 times. We sometimes achieve this optimization by wrapping the commands in a transaction. However, batching and transactions are different concepts. Transactions are about atomicity, and batching is about achieving economies of scale. This is what batching can look like when using a Go client library. The code change is not very complex. We just need to know that it happens to make things faster. Most of the time, it is also true that making a few expensive API calls concurrently is faster than doing them sequentially. Please note that I'm not talking about CPU-bound local computation here. I'm talking about dispatching concurrent work to the external world, and by which I mean outside of my current server component. In my case, the calls to service B are logically completely independent from the database calls and from the email operation. So I can decide to run service B concurrently and save some milliseconds. The 3 other operations depend on each other's completion, so I can't run them all concurrently. As the batch call to service B starts immediately and is already finished when the email has been sent, it's effectively become free. The total duration is the same with or without the call to service B. For this simple example of parallelizing 2 independent blocks of computation, I suggest to use a weight group. I don't recommend channels for this because the channel's details are subtle and tricky to get right. Weight groups are straightforward. There are only 3 methods to know: add to increment, down to decrement, and wait to let the main Go routine move on when all the tasks have completed. Now, please ask yourself if the email sending operation is more synchronous or asynchronous by nature. In my opinion, if sending an email can temporarily fail for some reason, then the user can't do much with that information, and it is the server's job to retry in a few minutes. I suggest that we add the email operation to a task queue using Google Cloud Tasks, and then return immediately, once again saving precious human milliseconds. The task will be executed asynchronously after the HTTP request has returned, and it will deal with the retry logic in case of an error. Differing some work with Cloud Task has nothing to do with the Go keyword differ. It's totally different. It's also more code than just launching a new Go routine. Creating an asynchronous task typically involves serializing some parameters into the payload of a HTTP request that will be processed by another handler of your app. Now let's pause and see the result. A total of 200 milliseconds instead of 900 is a huge win. You can see that this was achieved without using any low-level assembly code, without upgrading the underlying hardware, and without even caring if we have one or many CPU cores. In general, it is most useful to run the performance tests on the same machine configuration as used in production. Keep in mind that public clouds offer virtual machines, which are convenient, but don't give you full control over the underlying hardware. Even if you achieve very good average latencies, you may experience higher variance than with dedicated hardware. This may perturb the tests, and in some cases, this may perturb the user experience. My application written in Go creates a mosaic in which each tile is a colored cat. Because of copyright concerns, my input image will be Mona Lisa, and the little cat is drawn by myself. I need to specify two parameters, the resolution of a tile in pixels. Can we please switch to the demo? So the two parameters are the resolution of the tile in pixels and the number of tiles that will make the width of the resulting mosaic. So here I deployed this web app to App Engine standard, and I will request a low horizontal resolution of 20 cats only, and I will upload a picture of my girlfriend, Mona Lisa. Let's generate it. Spoiler alert, it should work and it should be fast. Yay, here she is. Okay, we can't see everything on the screen, but it looks a bit like this. It's really nice, but I don't recognize anymore the face of Mona Lisa. So I will try again, but this time requesting an horizontal resolution of 80 cats. Can't remember if this is slow or fast with the Wi-Fi. Server error. The server encountered an error and could not complete your request. I knew it. Let's have a look at the logs. That's part of the demo, trust me. So what does it say? That's an error, and it says exceeded soft memory limit of 120 megabytes because the F1 class of App Engine instances don't have very much memory. So to produce a big image, that's a problem. So I deployed the same, just changing the parameter of the instance class. That's vertical scalability. I will choose the biggest instance available in App Engine standard. Let's do the same in another window. Where is it? Here it is. So I requested an horizontal resolution of 80 cats. So this might take 10 or 15 seconds, but spoiler alert, it will work in the end. Yeah, here she is. And if I click to zoom, she's made full of little cats. This is great. And this would make actually a very good background picture. But if I wanted to print a poster to upload to a poster printing company, I would need a really high resolution. So for this, I would ask for more cats, 120 cats. That is not the total number of cats, of course. It's only on each line. And of course, for printing, I would need all the cats to be at least, let's say, 128 pixel width. Let's generate. Spoiler alert, it will fail, but it was planned. Okay, let's let it fail. And the error message will look just the same. I have exceeded the memory of the instance of 1 gigabyte. So what do? I deploy the same application to Kubernetes engine. Okay, let's open the app. And I will request 120 cats wide and 128 pixels wide for each cat. with that, I should be able to print a poster at least 2 meters high. That's my goal. So it will take a while. Meanwhile, I can show you that it's really a Kubernetes cluster. So yes, I have a cluster. Check. I have a Kubernetes GKE service. Check. I have a GKE workload, whatever that might be. And I have the deployment details of the underlying compute engine machines. Where is that? Maybe I'm not on the right screen. Yes, the VM instance is here, and I can see that each of my nodes have 8 virtual CPUs and 50 gigabytes of memory. 50 gigabytes, that should be enough to produce Mona Lisa. Yes, she's being generated. That is so huge. I will be able to send that file to the printing company. And if I want an even higher resolution, then I wouldn't use a web browser, because displaying a multi-gigabyte gigapixel pictures in the browser, that doesn't end up very well. But I can use curl for that, because the server in GKE will handle the load no problem. And I will get my huge files with many billions of pixels and send that for printing. OK, very cool. StackDriver profiler. So I'll open it, and I'll explain in a minute how to read that. So with very little extra configuration, I can have a profiler agent collect more information about what is going on in the CPU and in the memory of the compute instances. So here I will filter by today, 1 day, and I will take the top 5% of what happened. Wait, top 5%. OK. So this is the flame graph of the mosaic computation, the Mona Lisa with cats that we've seen. And we'll see in a few minutes how to read this. But basically, there is a process function. And inside the process function, my code is in another function, colorize cat. And quite a lot of the time is also spent on coding to PNG. But that will be in a few minutes. So cold starts. There are a true performance concern in serverless applications. A cold start is a request response that is much higher than usual because the server is warming up. This happens either because the app has very low traffic and the first server instance has to start, or because the traffic is increasing and the autoscaler decides to start an extra instance. In my experience, Go applications tend to have fast cold starts as they don't need a JVM, and also because thanks to the standard library, they usually don't need to load hundreds of megabytes of library dependencies. For example, my Go apps deployed on App Engine standard have a cold starts that are under 2 seconds. And 2 seconds only, that's a pretty good cold start. A last word about serverless. We've just announced Cloud Run this week, which lets you deploy your own containers to our serverless platform. And this is huge on so many levels. More specifically, with Cloud Run on GKE, you can achieve vertical scalability by choosing your custom machines with more memory and more CPU cores, and still scale to 0 in a serverless way. Now, let's have a look at the Go tooling. The tools that I'm going to show are not specific to the cloud. They can run on your development laptop, and they run on VMs as well. It's perfectly fine to do some performance exploration on your own computer, but remember that it's more relevant to run them in a production environment. Also, the measurements in production sometimes dispel the workstation measurements, as well as my best intuitions. In Go, this is how you run the automated test. All Go programmers are familiar with this command line. I encourage to explore performance in test files, as the standard testing package plays very nicely with the performance tooling. My demo today will use Go test, but remember that the same tools can be used for any Go executable or server. And this is how you run your benchmarks, integrated in the Go test subcommand with an additional flag. This is a powerful performance feature of the Go tooling. Write two benchmarks calling functions A and B respectively, and see which one of the two is the fastest. So these are two functions A and B. They do the same thing. They are trying to determine if the word database, here it is contained in this article here. So, spoiler alert, the answer is yes. The word database is here. And here are the unit tests. They check that it is true indeed. And here are the two benchmarks for A and B. So, let's run the test. Yay, they work. They pass. More specifically, test A and test B are passing. This is good. Now, let's run the benchmarks. So this is telling us that function BA was executed 10 million times and took on average 220 nanoseconds. And function B was executed 20 million times and took on average 100 milliseconds. Which means that in this case, string.contains is twice as fast as a regular expression, which is good to know if we want to decide which one to put in production. Trace. This is an execution tracer. It works by instrumenting the program to produce a binary file containing the activity of each CPU core over a period of time. Is the CPU idle? Is it running the garbage collector? Is it running a function? And what is the call trace? This is a CPU-bound sequential task. You can see that only one of the CPU cores is active, and the other ones are idle. And it turns out that the same sequential computation may be dispatched on several CPU cores by the scheduler of the Go runtime. This doesn't involve any concurrency. Only one CPU core is working at any given time. Now, this is an example of a concurrent computation using several Go routines. You can see that all the cores are busy. This can be good or bad, but it doesn't mean that the program is efficient. Having a lot of Go routines communicating and synchronizing with each other can lead to contention and to a lot of expensive context switching. That wasn't supposed to happen right now. Quite often, an inappropriate granularity for the Go routines can lead to worse performance with 4 CPU cores than the same sequential task on one single CPU core. The best multi-core performance is achieved when each Go routine performs a fair amount of sequential work before writing to a channel or releasing a mutex or decrementing a weight group. So I'm going to run the benchmark once again, but this time instrumented with the execution tracer. And outputting a binary file a.out. OK. This, by the way, these are the benchmark of the mosaic generation with the cat and Mona Lisa. OK, great. Now let's view the result. Go to trace. HTTP 6060, that's for my window on the right, and the file a.out. OK. So what do we have here? Quite a lot of information. So at the top, we can see at any, the X horizontal axis is the time, that's a few seconds. That's the duration of my benchmark, because my code is executed over and over for a few seconds. So we can see at any given time how many Go routines existed here. We can see the heap, so how much memory was actually consumed in orange and available to the Go runtime, that's in green. We can see how many operating system threads are running at this instant. And below, for each processor, for each CPU core, we can see if it's busy or idle, and we can see what it is doing at that time. So if I click anywhere here, can we read? Yes, we can read a little bit. So it was, at that time, encoding some PNG using the standard library. OK. So if I go to another slice, you can see that only one CPU core is active because my code is sequential. So here it's also encoding some PNG. Here it's decoding some JPEG. Oh yes, the input Mona Lisa, that was JPEG. OK. So, and there are 4 lines of processor because I have 4 CPU cores on my laptop. Now pprof. Pprof is the profiling data format available out of the box in Go. Let's have a look at the pprof CPU profiler. The CPU profiling works by sampling. It incurs a relatively small runtime overhead. Every now and then, the kernel sends a pprof signal, and the special handler of the Go runtime gathers the call trace of one currently running Go routine. The dataset of all these call traces over a period of time contains rich statistical information that is used to produce a graph of the function showing who calls who and how much time is spent in each function. In the resulting graph, each box is a function and explicitly displays the number of seconds spent inside the code of the function, the total time spent in the function including its own function calls, and the equivalent percentage of the total execution time recorded. Running the benchmarks is a very effective way to gather this information, as the functions are called many times over a short period of time. At the top, you will find the program's entry point and your own important functions. And at the bottom are all the standard library functions and the system calls. The duration of each box consists in the sum of its own CPU time plus all the CPU times of the function it calls. This counts only the time actually spent using the CPU, not the time spent waiting for something. OK, so once again, I will run the benchmarks. This time instrumented with the CPU profiler of pprof to a binary file a.prof. And it's important to not care at all about the results, the number from the benchmarks. These numbers, they are skewed by instrumentation. Here, I'm only interested into the visualization. Go tool pprof, OK. HTTP 6060, that's for my window on the right. And the binary file a.prof. OK. So what can we see? We can see that in my benchmark, the process function, which creates the mosaic, took 90% of the total time. OK. My own code colorized cat, it took only 19% of the total time. And the PNG encoding, which is a part of the standard library and which happens only at the end of the processing, it accounts for 53% of the total time. This is highly valuable insight. If I wanted to optimize my own code, I would only be able to optimize less than 20% of the workload. The bottleneck is the standard library function of PNG encoding, which is not my code and which I can't really parallelize on multiple cores because it is called only once at the end of the mosaic generation. However, now that I know that the encoding is a bottleneck, I decide to not buffer the output. The only advantage of buffering in my previous code was to lock the precise number of bytes written. That was the length of the byte buffer, the byte buffer. If I give the response writer directly to the process function, the browser will now receive the streamed data as it is being encoded. This is a good UX feedback because the user sees the first kitties displayed much sooner than before. And it also greatly improves the total response time because the encoding is effectively parallelized with the response data being downloaded by the client. I'm missing a slide. OK, no problem. So as I mentioned earlier, everyone has intuitions about expected performance. There is also sometimes some emotional investments and some prejudice on this topic. I suggest to stick to the facts and to discover the current bottleneck. What takes the most time in my use case? Everything that is not the bottleneck can wait. Now the flame graphs. A flame graph is a fancy way to visualize the profiling data. It was invented by Brendan Gregg around 2013. It is so I will run just the same command as before. Go to pprof with HTTP 6060. I cannot just rerun the same. I have to write it all over. And a.prof. OK. So if I click in View Flame Graph, I have this, which is really nice. It is not completely obvious the first time we see a flame graph, but the horizontal axis, x, doesn't represent the chronological time. However, the width of each span is proportional to the total duration spent executing this function. So here I have two benchmarks, benchmark process and benchmark process in memory. If I click on this one, I can see that my own code colorized cat is only part of the total. Decoding the JPEG of Mona Lisa is like 15%, and the PNG encoding at the end accounts for more than half. So if I am curious and I want to know what the standard library is doing while writing the image, I can dig deeper and deeper. So it is really great to find the root cause of some latency. Do we have at least 7 minutes? Yes, we do. OK. Why should I look at a flame graph if it basically displays the same information as the regular pprof graph? This is a stereotypical work day. Work in the morning, work in the afternoon, and sleep all night. And this is a stereotypical vacation day. Sleep in the morning, go to the beach in the afternoon, and dance all night. And this is what the pprof graph looks like if you run a simulation containing some people in activity and some people in vacation. Some functions, for example, sleep, are called by everyone, but not at the same time of the day. Even with a complete set of duration annotations, this graph doesn't give enough information to know if going to the beach, the yellow box, is part of work days or part of vacation days, or both. Maybe some employees prefer to skip work. This flame graph, built out of the same profiling information, quickly gives the answer. The beach activity on the right is properly stacked only under the vacation day box. And we also discover that a vacation day typically involves a bit more sleep than a work day. So the bottom line is flame graphs are very beautiful, like a campfire, and also super useful to find the root cause of latency issues. If you suspect that the performance of your program is not correctly explained by trace and pprof, you may want to use the perf tool, which is not specific to Go. Now, concurrency. And concurrency and parallelism are powerful tools to do several things at once and help decrease the total latency of a request. As we've seen, a lot of the time spent in a web service is spent waiting for an API call to return. In this case, the performance is not related at all to the number of CPU cores and not related to the speed of each CPU core. It is, however, extremely useful to be able to call several external APIs concurrently. I have to be quick on this one. This command, it runs the test. Who has ever run the data race detector? Okay, you already know about it. It's super useful to stay on track because when you work on performance optimization, sometimes you introduce concurrencies and channels and go routines, and you introduce subtle bugs, and it is really useful to detect those bugs as soon as possible. There is no such thing as a harmless data race in Go. We have to be careful. Here is a quick checklist of common performance bottlenecks and how we can address them in Go. The ever-popular execution of useless instructions. Obviously, hunting and eliminating useless code is a good idea. Please do it. Now, network I/O and external API calls are relatively extremely expensive. My advice is to make as few requests as possible and not to block everything while waiting for a network response. Reading from and writing to the file system is slower than most of what we do in memory and in the CPU. So my advice is to work as much as you can in memory and to do your I/O in a non-blocking way. I know some are taking pictures, but I'm running out of time. Contention. Thousands of Go routines waiting for each other is a perfect recipe for unnecessary sluggishness. To limit the excessive need for constant communication between Go routines, I suggest to create workers. The worker patterns, it looks like this. If I have 4 CPU cores and 1 million computation to perform, yes, I could launch 1 million Go routines, but that would be a little bit heavy and costly. It's more efficient to start a small number of worker Go routines, say 8, and have each worker process only 1/8 of the total load sequentially. Asking for memory to the operating system is a notoriously slow operation. My advice is to allocate large chunks of memory in a single call to the built-in make function, to reuse memory by passing buffers as arguments to the processing functions, and also using a pool from the sync package can prove very useful. Heap or stack. This part is specific to the Go compiler. We know that allocating in the heap is expensive and that allocating on the stack is almost free, but what goes in the heap and what goes to the stack? The answer is not intuitive. Some local variable may escape to the heap if we take its reference and pass it around. In the end, it depends if the compiler is clever enough to prove that a variable doesn't escape, so it is safe to put it on the stack. These commands prove scientifically that the Go specification does not contain the words stack or heap. Use this extra GC flag, -m, to determine which local variables escape or not. You may then try to adapt the function scope to leak less references. Regular expressions are great, but they are often overkill for a given need. So my advice is basically to avoid them when you can. Just 2 seconds and next slide. Function calls. A function call incurs a non-zero cost, which can be significant if the function is very small and called millions of times. So the specification does not talk at all about inlining, and the compiler has its own very specific internal rules when it comes to decide if a small function will be inlined or not. Chasing the inliner to have it inline a specific hot function has become a popular sport. Also, these implementation details are subject to change from a Go release to another. Before I finish, I'd like to thank my colleague David Gageot for his wonderful presentation tool DemoIt, which I'm using today. And also, why do I have 2 remote clickers? Because I'm worth it. Here is my takeaway. the Go language was designed for cloud computing with scalability in mind. Its ecosystem is rich, and the performance tooling is really good. Now, to improve the experience of your users and make the world a better place, start with an important use case, discover the bottleneck, fix it, and repeat. Thank you very much for listening.